now we have the presentation of Marco Aurélio, who will tell us about unbounded superradiance in regular black hole spacetimes.
So, good afternoon to everyone. So, is everyone hear me okay? The sound of my voice is okay? So, first of all, I'd like to thank the organized committee for the opportunity to present some of my works in this international workshop. As Carol already introduced me, so my name is Marco Aurélio, and today I'm going to talk about unbounded superradiance in regular black hole spacetimes, which is a work that was done in collaboration with Professors Leite, Dolan, and Crispino, who is my advisor. And so let's move on to. So I divide this presentation in 4 parts. So the first part I will talk about superradiance in black hole physics, just a quick introduction to put everyone at the same page. Then I will talk about the absorption parameter space, essentially to construct the absorption parameter space for the total absorption cross section. I will clarify every details in the next slides. Then I will discuss a little bit about the unbounded superradiance, which is the main result for this presentation here in particular, and then some concluding thoughts. So let's move on to the superradiance in black hole physics. So in simple terms, superradiance is a phenomenon that occurs when a wave is scattered by the black hole with more energy than it originally had. So to consider a very simple setup to see what is superradiance, you can consider, for instance, a spherically symmetric black hole, and which can be, for instance, the Heisenostrom black hole, which is described by the mass and its charge. So, and we need a scalar field, for instance. Can be a scalar field given by this psi omega L, where omega is the frequency and L is the angular momentum of the field. And this scalar field in particular is characterized by 2 parameters: its mass and its charge. So we label the mass and charge of the scalar field with mu and q, and we use capital M and capital Q for the mass and charge of the black hole, right? So let's suppose that this scalar field is coming from infinity towards the black hole, and when it comes to the black hole, it interacts with effective potential given by this function here, V of R, and it is partially transmitted into the black hole and partially reflect back to the infinity. So this is essentially one of the very simple setups in the context of the black hole physics that you can have superradiance. So under certain circumstances, this scalar wave here, this scalar field, can be scattered by the black hole with more energy than it originally had. And as a matter of fact, you can construct the absorption parameter space of the Heisenostrom black hole. So essentially, this absorption parameter space will tell us what happens with the total absorption cross-section. And the total absorption cross-section is in very simple terms, is defined as the amount of the scalar wave that is the ratio between the amount of the absorption of the scalar field that is absorbed by the black hole to the total flux that is going towards the black hole. So in the Heisenostrom case, we have essentially 3 possibilities for the total absorption cross-section. So we can have unbounded absorption, so the total absorption cross-section diverges positively as the frequency tends to the field mass. We can have a bounded absorption, so the total absorption cross-section is finite in the low frequency limit. And you can have the bounded superradiance, so the scalar wave can extract energy from the black hole, but the total absorption cross-section is still finite. So this is just to summarize some well-known results from the literature. But the question that I want to put here is, how is the absorption parameter space, how is this figure here, in the context of regular black holes based on nonlinear electrodynamics? So to put this in perspective, we need to consider a regular black hole, and for this presentation, we will consider the Ion Beato Garcia regular black hole, which was the first regular black hole solution obtained in the literature. So essentially, regular black holes are objects that are free of curvature of curvature singularities. And the nonlinear electrodynamics is a kind of source that we use to obtain such kind of objects. The main idea behind the nonlinear electrodynamics is an attempt to generalize Maxwell's theory for strong electromagnetic fields. So I will not give much detail about the origin or the construction of regular black holes and nonlinear electrodynamics, but Thursday, by the morning, Aurélio Jr. and Luis Leite will talk a bit more about these things. So let's move on to the absorption parameter space. I need to show to you guys how to construct the absorption parameter space. So the radial equation associated with the propagation of the scalar field can be written as given by equation 1. So this is the field that I have already discussed with you, and R star is the radial coordinate. So the effective this potential function is given by this expression given by equation 2, and a bit more of we need some attention in this term here, because here we can use the second term in the right hand side of this equation to show the critical condition for superradiance. So A0 is essentially the radial electrostatic potential, and when the frequency is equal to the product between the field charge and the electrostatic potential evaluated at the horizon, we have what we call by a threshold for superradiance or critical frequency. When omega is less than this critical frequency, we have superradiance. So in this case, for omega less than omega c, which is the critical frequency, the wave can extract energy from the black hole, right? So the metric function, just to show to you guys, of the Ion Beato Garcia regular black hole is given by equation 3. And I forgot to say, but this is all. Okay, this is all all the spherically symmetric case. So the wave satisfies the following boundary conditions that I have already discussed with you. So this is just like to put in perspective. I will say in a couple of seconds what is this parameter zeta and kappa. So these are the transmission and reflection coefficients, and they satisfy this equation here, where zeta is given by this expression here, and kappa is given by this expression here. So the total absorption cross section, which is the ratio between the amount of the scalar wave that is absorbed by the black hole to the total flux, can be written as given by equation 7. So to do that, we basically use the partial waves approach. So decompose the scalar wave as a sum of partial waves, right? So from now on, I will talk about, when I refer to the scalar field, I will refer as a scalar wave, not a scalar field. So to obtain the absorption parameter space for the ABG black hole, you can define a new potential function, which is given by equation 8. So this is minus the original potential function evaluated when mu is equals to omega. And at infinity, this equation behaves as equation 9. And with this equation, you can define two separatrices that will help us to build the absorption parameter space. So when the product between the masses is greater than the product between the charges, the Newtonian attraction dominates over the Coulomb repulsion. And this actually will define the bounded, unbounded boundary of the total absorption cross-section. So if the product between the masses is greater than the product between the charges, we will have an unbounded total absorption cross-section. And the other way around, we have unbounded absorption. And this happens because in this case, when the product between the charges is greater than the product between the masses, the Coulomb repulsion counterbalance the Newtonian attraction, and you can have a finite total absorption cross-section. So, and the second possibility is related with the superradiance threshold, which is given by, so basically this will define when we have the amplification due to the superradiance, or when we will just have the absorption without superradiance. So you combining these two separatrices, we can build the absorption parameter space for the ABG regular black hole. And so now we can see that we have three regions. So we have the The unbounded absorption, so just to be more clear, this red line here, this red line curve here, is the condition for superradiance. Basically, the condition for superradiance. And the blue curve here is the condition for the attractive repulsive threshold. This is basically when the product between the masses equals to the product between the charges. So the Newtonian the Newtonian is equilibrated with the Coulomb repulsion. So as you can see, for the regular black hole case, although we have the unbounded absorption and the bounded superradiance as it is in the Haise-Nordström case, for the regular black hole case, we have a new region which we call by unbounded superradiance. So recall that in the Haise-Nordström case, we have bounded absorption, but now here we have an unbounded superradiance, and that means that the total absorption, and what we can do to better understand what is going on here is try to analyze the total absorption cross-section. So in our paper, we have analyzed all the possible situations, but here we just show what is possibility the most interesting result. So these colored dots here, blue, purple, and different colors, are essentially points in this diagram that we can compute the total absorption cross-section. And when we compute the total absorption cross-section, we obtain that the total absorption cross-section for the situations where we have where we have this unbounded superradiance region, it actually, the total absorption cross-section is diverges as the frequency tends to the field mass, and is unbounded from below. This means that in the regular black hole case, in contrast with the Haise-Nordström case, we can have unbounded superradiance, which implies that we can have superradiance stability. Recall that in the Haise-Nordström case, superradiance stability in this setup with a field with mass and charge is only possible if you confine the Haise-Nordström case into a cavity. But this is not the case for the regular black hole case. We don't need a cavity to have unbounded superradiance or superradiance stability. So to conclude, we have studied superradiance in the context of regular black hole spacetimes based on nonlinear electrodynamics. We have obtained the absorption parameter space. So we have seen that in the case of the AWG regular black hole, we have an unbounded superradiance scenario. And we have found that AWG regular black hole can trigger superradiance stability. Just to point out some future perspectives and ongoing research, so we can for instance study the quasi-bound state spectrum. This was already done, and Luis, you're going to talk a bit more about it. So we can also search for general conditions considering arbitrary models, in the sense that so instead of considering a particular model of regular black hole based on nonlinear electrodynamics, let us try to consider an arbitrary model and try to search for what are the general conditions to have unbounded superradiance or superradiance stability. And finally, we can also investigate the Penrose process for the AWG regular black hole in detail. So this is, in simple terms, you can understand the Penrose process as the particle picture of this we are doing here. So it'd be interesting to analyze the Penrose process for this case. So these are my acknowledgements. Thank you all. That's it. Thank you.
Thank you, Marco. Any questions?
Thank you for your presentation, Marco. Can you go back to the frame 7? Frame 7. Well, in this frame, you define what you call separatraces, but I'm not familiarized with the concept. Can you explain it a little bit?
It's just basically a way to say that this separates two different boundaries in the absorption parameter space. It's basically that. Because, for instance, so let's consider this first one here. So when the product between the masses is equals to the product between the charges. So this, in the absorption parameter space, will define a line. right? So above this line we have unbounded absorption, and below this line we have bounded absorption. So now if you go to the second one, this second one here will define when we have above this line we have just absorption, and below this line we have superradiance. So when you combine these two things, so above the blue line we have unbounded absorption, below we have bound absorption. So now let's go to the second separatrices. So in the second one, above it we have just absorption. So combining these two one, we have unbounded absorption, and below it we have superradiance. So combining these two things, we have these two different regions: unbound superradiance, which is between the two separatrices, and we have the bounded superradiance, which is below the blue curve. So it's just a way to label things. Yes, in both cases is absorption, but it's just a way to label what is going on. So in both setups we have absorption, but the thing is that in the second case, the absorption presents the amplification, so it's related with superradiance.
Any more questions? You have to come here.
So I think one of the advantage to have a spherically symmetric setup as this one is that you can consider back reaction into the geometry in not a very hard way. I mean, like you would do in, let us say, rotating frame, right? So have you guys tried to look into that? Because, for instance, I don't know, you didn't show the vector potential or an equation for the vector potential or anything like that, right? So that would be an interesting thing to see. And this is also has been done for the case of Heisenberg black hole, is to see how is the charge extraction in this case, especially considering the instabilities that you guys have in the scenario. Have you guys looked into that or no?
So we didn't actually. We have regular expressions for the vector potential and all the quantities that we need to compute, but we haven't looked to that yet. What we have done, I think this is in our second paper. We have computed. No, it is in the first one. We have computed the amount of the energy that is extracted by the black hole in the linear case. So, but we have already thought about doing this. If you consider the back reaction of the scalar field, to see what happens if you solve the field equations considering the scalar field. This is something very interesting to do, especially if you eventually try to analyze some things around the black hole and so on. So. Yes, an electric charge.
So that's why you can combine with charge of the scalar field.
Yes. We have only considered as far as I know, actually, this is the first work considering superradiance in the regular black hole case, and most of the works they have searched in the literature, they work with superradiance considering electric charge. So we decide to work with the electric case. But I suppose that it's possible to work with the magnetic case. So, but some things probably changed in the setup.
For sure, there is zero, for instance, if you consider the potential. So in there you have an interaction between the charge and the electrostatic. Right?
Yes.
That will change because in the magnetic case there is no
Yes. But this is something interesting to look for.
Okay, so let's thank the speaker again.